Let's try what we just learned about comparison tests to this series or sequence. We need to come up with a new, hopefully simpler function sequence that we can reason about and know whether that sum converges or not. So how will we do that based on this? So what's our new sequence? Let's look in the numerator. We see n grows linearly. E to the negative n decays exponentially. So which one of those dominates? Which one makes the numerator get bigger and bigger faster than anything else? Well, this one is actually making the numerator smaller and smaller, so that's not going to dominate. So the n term here dominates. So we're going to ignore the e to the minus n term. Not permanently, just to make a new sequence. In the denominator, the n cubed term dominates. Like if you have n equals 100, what's 100 cubed? That's 10 to the 2 times 10 to the 2 times 10 to the 2, so 10 to the 6. So that's a million if n is 100, where this is just 10,000 times 7, nowhere near a million. So as n gets bigger and bigger, the n cubed gets big so much faster than the rest of these, it's almost like the rest of these aren't around. So n cubed dominates. So our new sequence, we're just paying attention to the dominant thing, so it'll be n over n cubed, which of course we could simplify to 1 over n squared, which is kind of handy. How does the new sequence compare to the original? Well, let's just look at the denominator. We know that n cubed is less than n cubed plus 7n squared plus 8n plus 13 because n is positive, so these values are all positive. Actually, wouldn't hurt to write that since n is bigger than 0. So if I take 1 over each of these, I get 1 over n cubed is then larger than 1 over n cubed plus blah, 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 blah. Because this denominator is smaller, so the fraction is larger. We can then put in this, like multiply both sides by n. And then what about the e to the minus n? Well, if I throw that in, I'm making the numerator smaller, so I'm going to get a smaller answer than all that. So here's my new sequence, and here's my original. So I know my new sequence is always bigger than my original sequence. So it wouldn't hurt to graph it carefully in Desmos, but we know it should look something like this. The original there, and then the new sequence there. And so what else can we say? The new sequence, sum n equals 10 to infinity 1 over n squared. You could write it as 1 over n squared or n over n cubed, same thing. Does that converge or diverge? Let's think about that. We could say it's a p-series with p equals 2, so sum converges. And since our new sum converges and the original is less than that, it also has to converge. So by the direct comparison test, the original sum converges. Since the original is less than the new and the new converges to a finite value, the original can't be infinite if it's less than a finite value. So that's a straightforward use of the direct comparison test. But here's the question. What if our sequence was something like n cubed? I'm going to leave off the e to the negative n altogether now. What if it was n cubed over n cubed, sorry, not n cubed, just n, or n cubed minus 7n squared plus 8n minus 13? If we try a direct comparison test, what's going to happen? This minusing will mess up this part of it, where we won't be saying, well, I've got all positive terms here. There might still be some n where we could guarantee that one was greater than the other, but we could say it's not as easy to know. So we could say, is n cubed still less than n cubed minus 7n squared plus 8n minus 13, now that we have the minus signs in there? It seems like n cubed should still dominate, so we'd like to be able to ignore all those, but we wouldn't get a simple statement like the new is always bigger than the original. And that leads us into the limit comparison test that we'll talk about next.